So thank you again for the introduction. So thanks for this opportunity. So today I will be presenting optimal time partitioning in integrated sensing and communication systems. So in India, we call it ISAC, and it has many variants, JCAS, JSAC, and so on. So this work is a joint work with Abhilash. He's a PhD candidate at IIT Delhi, and this is in collaboration with Professor Swades, who is my thesis advisor, and Professor Sheshan. Okay, so what is platooning? So there has been a craze for autonomous vehicles like autonomous trucks, autonomous drones, and so on. And platooning is a very popular driving strategy in autonomous vehicles. So essentially, the vehicles are one behind the other, and they form a straight line, and they move in a straight line trajectory. So platooning ensures line of sight communication, and it is very useful in traffic planning and in developing vehicle to vehicle infrastructure. So equipping the platooned vehicles with object sensing and communication hardware is very essential for smooth movement. And ISAC has emerged as a very popular strategy in autonomous V2V systems. So the main motivation of this work is that the object sensing and data communication operations are influenced by many design parameters like transmit power, the communication channel gain, the range and velocity of the target, the time duration required for sensing and communication. So we want to quantify the optimality of the sensing and the communication time duration. It is what should be the duration required for sensing and how much time should you communicate. And we want to analyze the influence of sensing and communication design parameters on this time duration. And we want to study the coupling between the sensing and communication parameters, how they influence each other, and so on. So in this paper, we propose an optimal time partitioning OTP framework. So we study the trade-offs among the sensing and communication design parameters involved. We propose a sensing measure to model and quantify the radar sensing performance as a function of the maximum detectable range and velocity of the target object. We formulate the problem as a convex problem, and the problem is constrained by the performance guarantees of both sensing as well as communication. And we derive the optimal bounds on sensing and communication time duration, and we'll share some insights on the coupling of these performance measures. So we have a V2V system where you have a vehicle A, which aims to sense and communicate with a vehicle B, which is part of the platoon. So in this work, we are trying to understand a two-vehicle scenario. Of course, the analysis can be extended to multiple vehicles, and the system operates in a half duplex fashion. So half duplex meaning that when the system is sensing, it does not communicate, and when it communicates, it doesn't sense. The vehicle A is equipped with a transceiver. It has a transmitter and it has a receiver, and it sends the sensing and communication signal to sense vehicle B. And so the communication happens at B, whereas the sensing is happening at vehicle A. So that needs to be kept in mind. And there are time frames, and each time frame is having a sensing duration and a communication duration. And we will see what should be the sensing duration and what should be the communication duration. Okay, so the vehicle is at a distance r, and it is moving with a velocity v. As discussed, vehicle A has an ISAC transceiver comprising of a transmitter capable of performing object sensing as well as data communication. And it transmits a FMCW signal. So what is FMCW? It's frequency modulated continuous wave. possibly you want, shall I explain on the board? I think it's okay. Yes. Oui, pour soulever alors un peu le point.
Sorry.
I think I keep it at half. It's,
I don't know how to start. So is I can't do,
use the lower button.
okay, yeah.
I can't do both.
Okay, I think it's okay.
The big arrow. Which means that you can go up all the way, up, because the broad is wide. Just go up.
But it's not.
They're linked. So,
I think it's okay. So in general, if we have a frequency time analysis, so if we have a constant frequency with respect to time, so the idea is that if you have an object and it is emitting a sinusoid to detect another object, this is the transmitter and this is the object. So if the object is moving, so in that case, what will happen is that due to the Doppler shift, the reflect echo signal will be a little faster. So and if the object moves towards the radar, the frequency is positive, that is the frequency increases. And if it is going away, in that case, the frequency is much lower. So if we have a constant frequency or constant sinusoid, in that case, what happens is that the echo is also obviously constant, but it is shifted upwards or downwards depending on the velocity of the target. But in that case, of course, you can measure this frequency gap or the Doppler shift. So you can measure the Doppler shift. But in this case, the distance aspect is, we cannot capture the distance aspect. So that is why a ramp signal is used. So, so when you ramp the frequency with respect to time, so it is called a frequency modulated continuous wave. So you are constantly modulating the frequency. It's a linearly increasing frequency, and it's of a continuous wave, of course. So in this case, the echo, when you receive, the echo is time shifted, which helps to capture the range, and it is of course frequency shifted, which helps to capture the Doppler. That is why FMCW is very attractive. So the vehicle transmits a FMCW signal to another vehicle at the beginning of its time frame, and the vehicles senses vehicle B through the echo signal, as discussed, and while the data communication happens at the receiver of vehicle B. Okay, and the sensing and communication are carried out in a time division duplexed manner. And yeah, the sensing follows communication. So a question can be why communication doesn't happen first and sensing later. So this has a lot of advantages, because if you sense the object, you can use this sensing operation as well as for the channel estimation, which can help to improve upon the communication operation, which is following the sensing. So that is why sensing first is quite beneficial as compared to communicating first. So we propose a sensing measure as shown in equation 1, which is a function of the sensing bandwidth, the maximum range, sensing range, the maximum detectable velocity, the maximum, the sensing time duration, and the wavelength of the radar, which is lambda, and speed of propagation. So what happens is at the receiver of the FMCW radar, the signal is first de-chirped. So de-chirping is similar to demodulation, where the signal is multiplied with a conjugate of the same signal, and then you sample it to obtain a range Doppler matrix. Now, this range Doppler matrix is quite interesting, and if you have multiple uh, target objects, it can be very useful to capture the multiple locations of the targets. And each cell in this range Doppler matrix, we assume it to have a binary value. So 1 represents the presence of target and 0 represents an unoccupied target. So in equation 2, if that is equation 2 is the maximum capacity of FMCW radar, meaning that what is the maximum amount of targets which one can capture with n chirps, then what happens is that this is a function of m times n, with m being the maximum range bins, that is maximum possible target locations, and n being the maximum possible velocity levels which the radar can capture. So the idea of the sensing measure is to try to model the number of maximum range locations which the radar can capture, and the maximum velocity levels which we can capture. Also, it should be noted that currently we are having a isotropic antenna, so it is radiating at all levels. So of course, if we have a more planar array, then you can beamform on the specific directions if required. Okay, so the sensing measure is concave in nature. So you can see the variation of this sensing measure with respect to the sensing time duration, and it is concave in nature. And this is for we vary the R and V, that is the maximum possible distance and velocity, and we observe the sensing measure to be concave in nature. And
That's a question. So could you comment on these formulas that you propose for the equation one?
Yes.
Could you comment a little bit on that in terms of
how this came?
Yes, how
Okay.
to build this characteristics for the sensing quality?
Okay, so so we are focusing on the logarithm ensures the concave nature, and when you do m times n, which is this internal parameter, so it represents the total number of independent resolutions in a range Doppler matrix. So so this range Doppler matrix is very important. So this echo which is returning back, so this echo is, say it is some say xt, and which you transmit, and say you have the conjugate which it is multiplied. So it is something, say, like a sine at, and say some other sine bt. So what you get is some cosine a minus b, and some other cosine a plus b, right? So so we try to capture this difference of the transmitted and the echo, and this is called the beat frequency. So this beat frequency of the transmitted and the echo, if we are able to capture this beat frequency, and then if we sample it, say we have a 256 samples per second, or depending on some sampling rate, so you generate a matrix. So if you have a single chirp, you will get, say, a 1 cross 256, right? So now if you see this 1 cross 256, so this also determines it's kind of a, it depends on the wavelength, or what is the maximum range that you can sense. the target. And so if there are like zeros and ones, so you can make a reasonable guess that there is a object which is located at which distance, right? And if you send multiple such chirps, say you send some k chirps, so you get k cross 256. So this is my sampling rate, right? And this is the range Doppler matrix. This is what is called S. And the idea is again that so the rows, you can capture the range with the help of the rows, and you can capture the Doppler or the velocity with the help of the columns. So it forms a system of equations which can be solved if you send a lot of chirps. So that is the idea. So we have tried to leverage this m times n, as you can.
Yeah. So one question is that, I mean, there ought to be some noise structure, I suppose. I mean, so this is signaling there is a fading, there is multiple reflections, things like that. So
True.
what I don't understand is how the noise structure, it's a channel, right? So
Yes.
right there is a channel. So how is it linked to any information selection construct or?
Certainly, there will be noise. We have not. So it's a very ideal scenario in this
So
case.
you assume that the false alarm rate is equal to 0.
Yes. So we will. I'll show a sensing measure or sensing guarantee, which we got from literature, and which is quite useful. I'll just show. Just give me, yeah. So there is a radar range equation. So radar range equation is quite similar to the free path loss equation, which we have communication in radar. They have radar range equation. So to ensure this radar sensing performance in terms of false alarm rate and detection probability, this SNR of the received echo that should be considered. And this SNR of the echo is given in equation 4, which is a function of the radar cross-section of the target, the transmit power of its antenna element, the antenna gain, and so on. So the idea is that the optimal sensing duration should be greater than equal to some tau, which has some SNR threshold of the echo, right? So this reflected echo which is coming, it should have some SNR higher than some threshold. So I believe this can be useful in the mutual information possible analysis which you are asking. And this depends on the, so this is quite important, this radar cross section of the target, right? So I mean, broader the radar cross section, better is the.
So you have this KT damp BS. So that resembles something to do with white noise. What is BS?
BS is the sensing bandwidth. What is the?
So that is the bandwidth of the chirp signal?
Oh, yes. Yeah. At which you are sending the signal to sense.
And when you send multiple chirps, you mean it is in the same time slot, or you're talking about multiple chirps in multiple time slots?
So like you have a frame, the idea is that you send multiple chirps. A single chirp has, say, some 128 chirps. So it's called a CPI. So it's like a set of chirps which you need to send. And as I said here, you need to send a set of chirps so that you can make the range Doppler matrix. And the idea is how many chirps are required for efficient sensing duration, right? So that is what we are trying to capture, so that you can utilize the resource more efficiently, and you can also communicate possibly. So this initial time frame which was shown here, so this is having multiple chirps, right? So there are multiple chirps which are being sent, and we are choosing how many such chirps are required within a given time frame, so that the sensing operation can be successfully achieved. So yeah, so that is the concept. Is this clear? Okay. Then we have the communication model, and we assume a relay feeding channel. So there might be question that since there is line of sight, why relay? So this is like the worst possible communication model, right? So if we get some gains with relay channel, then Rician will obviously much better in terms of the communication requirement. So that is why we have gone with a relay itself. And yeah, so the performance guarantee for the communication, the performance guarantee, we have chosen a minimum data rate requirement for the.
I have a question. You use the frequency for sensing and communication. They are different frequency, right? Or they are the same frequency?
You mean the central frequency?
Because you use BS for sensing and BC for communication. Right?
Yes, so
Are
the bandwidths are overlapping, but it's not the communication is not wideband. So the sensing is over a wide band, and we have assumed 180 kilohertz for the communication, which is the normal communication subcarrier, 180 kilohertz. But this falls in the millimeter wave. The sensing bandwidth falls in the millimeter wave range. So yes. Okay. Yes. So the idea is that we don't want, if we have a full duplex, that is sensing and communication is happening together. So in that case, there will be interference. That is, the sensing will interfere with communication and the communication will interfere with sensing. And to avoid that, half duplex seems better. But of course, there is some lower throughput. But yeah, I mean, it's an open problem, full duplex models. So if we try to maximize this sensing measure with constraining it on the sensing guarantee and on the communication guarantee, right? So we obtain the sensing duration as a function of the communication QoS, right? So that is the key idea. I'll just show how the equations are arriving. So we first make the Lagrangian, and when you solve for the primal through partially differentiating with respect to Ts, we obtain the primal solution, and then we form the dual by substituting the primal solution, and we obtain the dual, which is shown in 11. And when we partially differentiate with respect to the dual variables, we get the, of course, Ts is tau, which is also, I mean, it's common sense, because Ts has to be greater than less than tau, which was the constraint. And this is the other value of Ts, which is a function of alpha. And this alpha is the communication QoS. So a corollary which we can give is on the maximum throughput.
So it was this fast for me. So could you explain how the sensing helps the communication? So it's some CSI, or so. What is the framework which is at the basis of the optimization? Maybe what do you bring by sensing to the communication?
So right now that is not happening, right? I mean, I can show in the results. So it's like a very basic. This framework is quite basic. So this does not. So in this framework, the channel sensing is not happening. But that is a motivation. Right. So, but I can show you the results, which are quite encouraging, which shows that the sensing time is adaptive with respect to the channel gain, and we have those results.
But can you then rephrase what the optimization? I missed what the optimization for is then. If there is no entanglement between the
So-
two.
The entanglement comes because of the total time frame. So you have a total time which is TC, right? This is the communication throughput, TC times and this is B log 2, which is the Shannon data rate. And this TC is T minus TS. So because the times are coupled and you have a total time frame, right, which is TS plus TC. So the times are coupled in some sense, and because the times are coupled, the communication throughput gets coupled with the sensing measure, sensing
What
guarantee.
what you are trying to optimize is, what is the minimum sensing time which you need, with which you will be able to satisfy the criteria of good sensing,
Yes,
and then that would be maximum time for communication. That
Right.
is what you are
True.
saying.
True. So, and this sensing measure is like how many targets I can sense at the same time with a reliably good SNR measure, right? And so that is the overall idea, that you don't need to, for an entire time frame, you don't need to keep sensing. And even if you sense much lesser, it is quite reasonably good, which I'll show in the results. Yeah, I think Go had a question.
What is K? Different K?
Oh, yeah. So, sorry. So we have tried to simplify this expression of sensing measure. So there is this K, which is 1 by natural log 2, and Ks is all these constants, right? And this is Ks. So it's just to simplify the variables. And similarly, when you have this Shannon rate, so this is 1 by log 2 was K, which was defined earlier, and this Kc is the constants of the communication parameters. So yeah, so
They are constant. They are constant.
yes, I mean that transmit power is constant, the power spectral density is constant, and the distance is I mean, for a given optimization, you need to assume they are constants, right? Okay. Yeah. So yes, so this was the formulation, and so this is concave, and the constraints are affine, and so this was a Lagrangian, and we solve it through Lagrangian dual method, and in the dual we get two solutions for TS. One is TS is tau, and one is what if TS is not tau, then much lesser than, sorry, much greater than tau, right? So this TS, the feasible region for TS is between tau and this value, which also comes from the constraints if you analyze the constraints. And so you get this bound on the data rate, how much data rate can you achieve. And this alpha, if you see, this is also a function of this tau now. So this is coupled in time. So I think which professor was asking how they are coupled. So they are coupled because you have a time frame, and they are coupled in time.
For the equation 15, because from equation 14 to 15.
Yes.
Do you think it's possible that this is not feasible because alpha has some minimum rates? So
No, alpha is your minimum rate, right?
this is not given. This is your objective.
No. The minimum communication QoS is predefined. What we want the system to achieve, right? Okay, so right, so that is alpha, right? And tau is how much time you require for sensing, so that the sensing measure can give accurate result. So for accurate parameter detection. So that is what is tau. Right? Okay, so the results. So first result is that if you observe with respect to distance, so as my distance is increasing, the communication time is increasing, and consequently the sensing adapts itself uh, to accommodate for the communication time. Right? Uh, so communication time increases with distance as well as with increasing velocity for a fixed distance to achieve the required data rate. The sensing time, of course, reduces, but so this is the tau which you can see at the bottom, right? So the sensing time reduces adaptively, but it is much higher than the tau which we have. The next, this might be interesting. So if you observe with respect to the average channel gain, so as my channel gain is good, I am requiring lesser communication time, and accordingly the sensing time increases, right? So there is again this adaptive coupling which you can see of the sensing and communication. And similarly with respect to communication transmit power, as my communication transmit power increases, the communication time requirement reduces, right? And adaptively the sensing time adapts itself and increases. So the optimal communication time decreases with increasing channel gain and increasing the transmit power. So Professor, this is what I was trying to say, that so this model assumes like we know the CSI, it is known beforehand, but if there is partial known, or if we don't know the CSI beforehand, then possibly this can be very beneficial to know the CSI information. So that is the idea. Next is communication throughput with respect to distance. So this is communication throughput. So what it is interesting is when the channel is bad, so when the channel gain is very low, at that time we observe that the proposed OTP framework gives up to 12% increase in the communication throughput over the equal time partitioning framework. So we compare results with respect to an equal time partitioning. So the sensing and communication times are assumed to be half or equal. So in that case, it's seen that when you have the ISAC framework, that is the sensing and communication are intelligent, at that time when the channel is poor, we get very good gains. For very short distance, up to 30 meters, we observe that the proposed framework is marginally lower, and that is because at shorter distance, the communication time is much lesser required, whereas more sensing time is required, and so it results in lower throughput. So that is the so again, so when the channel is bad, this is very useful to have the adaptive coupling between sensing and communication.
So you're saying shorter distance, the optimal communication time is longer.
So what happens is, so we are discussing about the communication throughput, right? So communication throughput is time into
optimal communication time is
is much shorter.
Yeah, and so that means for shorter distance, sensing needs more time.
Actually, so because the communication QoS is fixed, right? And if it's at a shorter distance, and again, there's an interplay between the distance and the velocity, right? So it may, in this case, what we observe is that it's marginal. But of course, we need to study this more. I agree. Yes.
Because I'm asking this question because it sounds counterintuitive. I mean, if the distance between the transmitter and the target is small, then sensing should be better, no?
Sensing should be
have
better, I agree, and it should it also requires a less communication time, right? Because of the distance is less. That is why the communication throughput, what is coming as compared to the equal time partitioning, right? So if you compare with equal time partitioning, what is happening is that, so I mean, equal time partitioning does not require, it is allocating more resource for communication.
Yeah, but.
But that resource is not.
What is behind equal time participation? What are the performance figures behind equal time participation?
So equal time partitioning is essentially that the time frame, the TS and TC are say 0.5 capital T, 0.5 capital T, right? So now what happens is, if you have a very short distance, so the optimal time is required actually is very less, right? So the corresponding optimal throughput is coming out to be lesser. And if you see with respect to ETP, so because ETP assigns more time resources, so the corresponding throughput is much higher, but we don't require that much throughput. That is what I am trying to highlight. That if I require alpha and through ETP, I am getting more than what is required, right? So that is why this is this abnormality is being observed, right? So I mean okay, so let me try to explain through this. So in this case, if you see you have the tau, which is much lower than the sensing times, which you are getting, right? So while the sensing time is reducing, but it is much higher than the sensing threshold. Similarly, in this case, what is happening? So we should have actually plotted the alpha in this plot. So we didn't plot alpha in this figure. That is why I think this confusion is arising. So Professor, the idea is that because this is a communication throughput, right? So the communication throughput which we are achieving is for good gain at shorter distance. I mean that we don't require that much of communication QoS. So, yeah. I believe if we increase the distance further, it will go down. Certainly. Yeah. So like so far it has simulated up to around 150 meters. So if we possibly say up to 500 meters, it will go down certainly. But then in an autonomous platooning system for which this application is, I mean, 150 meters between two vehicles is sufficiently much big distance, right?
But it's for sure it's something
I think we can discuss offline, no problem. So yeah, I believe that's it. Yeah, thank you.
I have one
Yes.
one question is I know that in your simulation the bandwidth for sensing is 1,500 times more than yes for communication. So why not? Well, it is possible to consider this parallel bandwidth is spent. You do it simultaneously, right? Because over the frequency domain, we are also going. You suppose you reduce 180
So
hertz for
the idea is that if you go for a wideband communication, then the inter-symbol interference also will have to be taken into account because in a wideband, the ISI increases, right? The symbol overlapping and the frequency selectivity of the channel increases.
No, my question is you don't use wideband you don't use wideband communication. You still use this narrowband communication. You modulate a very 0.1% of your sensing bandwidth for communication. Is it possible? for doing that, because the difference is very large.
So you want to allocate a separate chunk for of the bandwidth for communication and keep others for sensing? Are you saying something like that? I mean, you want to have some like partial frequency allocation. Are you proposing something like that?
Yes, the nature of it.
So, like even if the bandwidth sizes differ, but the center frequency is similar for the communication as well as sensing. So,
So what is exactly the signal structure the transmitter sends out?
it is
It's
a
a chirp waveform,
it's a chirp, yes.
and what is it, BC?
BC is the communication bandwidth.
Yeah, but how is it utilized? What is the signal that the transmitter sends to use this bandwidth which carries data?
Right. So the idea is to use the chirp itself only
Yeah.
in the broad sense.
Like we have in law.
Exactly. Like if you have the LoRa plus IoT system.
So then why did you in the very beginning talk about half duplex? I mean, it is the same signal which is used for sensing as well as for communication.
So half duplex concept is that when sensing is happening, communication is not happening.
Yeah, but the transmitter is always sending the same signal.
Yeah, FMCW signal.
Yeah,
Right.
which is modulated with
Yes,
certain information rate.
True.
Yeah.
True.
And the receiver at the target side
Mhm.
can demodulate all the information. Whereas for sensing, we need the echo to be.
So the problem, what might happen is if you are communicating while you are sensing. So this echo, which is you are receiving the echo, it might interfere with the communication signal.
Yeah, but so, but the receiver is at a distance.
Mhm.
Receiver which you are communicating and which you are trying to sense
Mhm.
is at a distance. It is not located with the transmitter.
Yeah, I agree that full duplex, in fact, will be more efficient, and that is the way forward in the future, because half duplex doesn't. So it is not very resource efficient, a half duplex system. So of course we will be moving towards full duplex if you want to visualize ideal practical integrated sensing and communication. So I believe it will be full duplex. Yeah. So this is a letter paper, so it's like short work, and certainly there are scope for improvement.
So I have another question. Your performance target for sensing, criteria for sensing, can you put that equation one again?
Sure. Yes. This is sensing criteria, right?
Yeah, sensing criteria.
Yes. So this is the radar range equation and the eco FNR. The sensing measure?
Measure.
Yes. Okay.
And somewhere you say that many of these terms which are behind AID, PS, PSR, and BM have been regrouped into a constant.
True.
But I mean, both velocity as well range, there is a range. These are not constant values.
I agree. So that is why we have in the results, we have tried to simulate for various values of R for distance as well as for velocity, right? So, I mean, so when you simulate, I mean, like when we simulate for a given iterations, so we assume fixed distance, fixed velocity,
So
and then
you take a snapshot and then
yes,
you do
yes,
the optimization.
that's true. Yes. So of course, but both will be random, and for random distances and random velocity between two vehicles, yes. But of course, this optimization has its own limitations, and yeah.
And you assume that one car is talking to the one just behind and that's it.
This is for a two-vehicle system, that's true. But if we have, say, a multi-vehicle system, there will be more challenges. For instance, the one at the back, it will also interfere, right? So there will be many more conditions to take into account. Also, there can be like some ghost reflections or ghost echoes which might increase the false alarm rate. So I absolutely agree with all that. There's a lot of scope to improve technically.
Any other question? Perhaps I have one more. This optimization problem, if you think of the line of thought where you would, by sensing, improve the CSI.
Yes.
And if you have an estimate of CSI which is good enough, then you would improve the communication.
Right.
So could you try to entangle the two things?
Certainly.
So another optimization problem where you would just maximize the rate, you would lose if you, of course, spend too much time to sense, but win because you have better CSI, there might be an optimal there.
So one go-to idea is that you play with the modulation, right? So if the channel is bad, you increase your modulation symbols, because this is eventually a chirp, which is a frequency modulated symbol. So you basically push more modulation symbols while you are communicating. If the channel is good, possibly even a lower modulation scheme can work better. So it is kind of a joint time and power play which is happening, which will be the future of this work if it gets extended, right? So the idea is that this is so far a time optimization. So we are not touching the power at all, right? So obviously, but the power will also play. So power is analogous to the modulation scheme. So certainly the modulation can be very adaptive, and so it's like a adaptive modulation encoding, which also takes the CSI into account. So AMC, the traditional AMC, in fact, is yeah.
And so that means that in your mind there is a way of posing an optimization problem which will maximize rate by a proper sensing.
But I think this current sensing needs to first take into account, say, multiple targets, take into account the interference, and of course that part needs to be improved analytically. And of course you have this adaptive modulation scheme encoding is obviously there. Yes.
Any other question? Okay, thanks. Ashutosh. Let's check there is no question. Okay. Thank you.
Thanks.